Okay, so we're gonna continue going through chapter 16. Does anyone need the notes that I handed out yesterday? So the main point was we found two ways to compute integrals over a line, right? So we had these scalar line integrals, which were integrating over a curve where we're integrating a function, or let me word that better. You're integrating a scalar function over a curve C. And this is given by this equation here at the top of page 2. So this is one equation you need to know. And then we also saw that you can integrate over a vector, or you can integrate a vector field over a curve as well. And that's given by this equation, which is at the top of page 4. So those are the two main equations you have to know. I didn't really give a lot of incentive or understanding in terms of like, what are you actually doing with the scalar line integral? So I wanted to look at a picture which illustrated what I was talking about yesterday in a way that's much better, right? And so what we're really doing here with these scalar line integrals is we have this curve, like this is where we're starting off with this curve I'm highlighting in red, right? This is the curve that we're integrating over. This is our curve C. And so this curve C gives us the collection of inputs that we're going to be plugging into our function f of xy. Once you plug in our points into f, you can get something that looks like the following, right? So this is the image of the curve. Let me do it like this, right? So I'm highlighting the image of the curve in blue. Maybe it's a little hard to see. Right, but this is f of c. This is like one way of writing it. This is the image of the curve after you apply f. And so when we're computing the scalar line integral, what we're really doing is just finding the area underneath f evaluated at this curve. So like what I'm highlighting in red. And so if you were to, I guess, project it onto the xz plane, what we're really doing is like this is kind of like the curve projected to the xz plane. This is f of c projected to the xy plane, so or xz plane, so you look something like this. And then the actual integral is we're finding the area underneath this curve. So that's what we're doing with the scalar line integral, right? We're looking at some subset of points on the xy plane. We're plugging them into f. They get a curve in 3 space, and then we're finding the area underneath the curve. That's what we're doing when we're computing the scalar line integral. And then when we're doing the vector field integral, it's really just a form of the scalar line integral, so the same interpretation kind of holds. And then we'll also be able to view vector line integrals in terms of physical concepts like work after we're done working through another example. Okay, so that's important to understand. Actually, I mean, I'm not going to ask you about that too much, but I mean, it helps to have an understanding, I guess, of what we're actually doing with these computations. Okay, so we're going to continue using this equation for 2 more examples before we go on to section 16.3, which is where we'll return talking about conservative vector fields. So this is the main equation again. If we're integrating a vector field over a curve C, you always do f of rt dotted with r prime of t, where r is the parameterization of your curve C. So we did an example of this yesterday to conclude class. Actually, we did 2 examples. We finished by looking at the vector or the vortex field and showed it always ends up being 2 pi. And so this next example is going to be a little bit more complicated. So for this example, I want you to compute the following vector line integral over the curve C, where we have that the vector field f is given by e to the z, e to the y, and then x plus y. And then we have that C is a triangle joining the points 1, 0, 0, 0, 1, 0, and 0, 0, 1. So it's what we have pictured here. And then it's oriented in the counterclockwise direction when viewed from above. So it's indicated by these arrows, right? And so this is a harder problem in the sense that we're really looking at 3 different curves here, right? C is really the union of 3 curves. We have this curve here, which we can call C1. We have this curve here, And so C1 is going from 1, 0, 0 to 0, 1, 0. We have this curve that goes from 0, 1, 0 to 0, 0, 1. And then we have this curve that goes from 0, 0, 1 to 1, 0, 0. So this is C2, this is C3. So really we have that this integral of f over c, this is really going to be equal to the following sum. It's going to be the sum of C1 of f dotted with dr. This is C1 plus the integral of C2 f dot dr. And then that's going to be plus the integral over C3 f dot dr. So we really need to compute 3 integrals here, which is kind of annoying. But you'll see they all kind of play out in a similar way. And so what we need to do is we need to determine these parameterizations of these curves, right? It doesn't tell us anything about the parameterization, so we need to figure that out. And so let's just focus on C1 initially. Let's just focus on C1. Let's first determine what this parameterization is going to be. And so the way of thinking about this is we're starting at the point 1, 0, 0, and we're concluding at the point 0, 1, 0. And so we need to have that when t is equal to 0, we get x is equal to 1. And when t is equal to 1, we have that y ends up being equal to 1. And so one way of thinking about this is the following. So I'm going to say this is like R1 of t. One way to make this happen is you can define this to be the following. So we can have 1 minus t in the first component. We can have t in the second component. And then z is always equal to 0, right? We're on the xy plane, so z is always equal to 0. So this is equal to 0. And so if you think about it, if we plug in t is equal to 0, we get the point just 1, 0, 0 here. And then when t is equal to 1, when t is equal to 1, we get 1 minus 1, which will be 0. And then you get 1 here, and then this is going to be 0. All I'm doing, like maybe it's confusing in terms of like, where am I getting this from, right? All I'm saying is like, you can think about this as being the line y is equal to 1 minus x, right? And so really like, I'm just saying like, if y is equal to 1 minus x, or you can, I mean, analogously, this implies we have x is equal to 1 minus y, right? So I'm saying like t is equal to x. Oh, wait, never mind. I'm saying t is equal to y. Sorry, I'm not explaining myself very well. I'm saying like t is equal to y. And if t is equal to y, that means x is equal to 1 minus t. That's like another way of thinking about this. All right, so this is what the parameterization of this line is going to be. I think it's easier to just think in terms of when t is equal to 0, we need the point 1, 0, 0. This would work. And when t is equal to 1, we have to have the point 0, 1, 0. So like this, again, would end up working. And so now we need to apply, if we want to find this integral, we need to find the derivative of this. And then we also need to find the composition of f with this curve. And then we need to take the integral of the dot product. And so if we take the derivative of R1, you just get the following vector. It's just going to be minus 1, 1, 0. And then if you do f of R1 of t, this is going to be equal to f evaluated at 1 minus t, t 0. So we're going to get another vector field out of this. And so if you look at f, the first component of f is e raised to the third component. In this case, the third component is just equal to 0. So this is going to be 1. The second component is e to the y, where y is the second component. So it's going to be e to the t. And then the third component is going to be x plus y. In this case, x plus y is going to be 1 minus t plus t, which is just equal to 1. Right, so this is the composition of f with this curve R1 of t. And now we take the dot product of this curve with the derivative, right? So we have that this integral over C1 of f dot dr, this is equal to the integral. So we're going from t is equal to 0 to t is equal to 1, and it's going to be f of R1 of t dotted with R1 prime of t dt. And so if you take the dot product of these two vectors, you're just going to have 1 times -1, which will give you -1, and that'll be plus e to the t times 1. So it's really just going to be e to the t minus 1. So this is equal to the integral from 0 to 1 of e to the t minus 1 dt. And then if you take the integral of it, it's just going to be e to the t minus t. You plug in 1, so it ends up being equal to e minus 2. Because when you plug in t is equal to 0, you'll get a minus 1 out of this. So this will end up being equal to e minus 2. Okay, so this is why I don't like this problem. So we're 1/3 of the way done. You have to do this for the other two paths that we have. So this was only this part of the curve. We still have to cover C2, and then we have to cover C3 as well. But they're going to be computed in a similar way. Usually when I do tedious problems like this, it means that in the future, we'll have an easier way of solving it. So I'll tell you, like, after we learn Stokes' theorem, like what Stokes' theorem is going to allow you to do, this is section 17.2, is instead of integrating over these three curves via 3 separate integrals, you can instead do the same computation as a single double integral over this region of the plane right here. So I'm making it tedious now, so that way when we learn Stokes' theorem, we can have like an appreciation for it, I guess. But for now, we don't know Stokes' theorem, so we're just going to rely on doing it the tedious way. The next is going to be C2. C2 is pretty much the exact same idea over again. We're starting at 0, 1, 0, and we're ending at the point 0, 0, 1. So just like we had before, we have R2 of t. This is going to be equal to 0, t, and then 1 minus t. So when you plug in t is equal to 0, you get 0, 1, 0. Oh, wait, I did this backwards. This should be 1 minus t in the second component, and then t in the third component. So that way, when you plug in t is equal to 0, you just get 0, 1, 0. If you plug in t is equal to 1, you get 0, 0, 1. And then I'm kind of just going to write out. I'm not going to go into as much detail as I did before. Right, so r prime of t here, this is going to be equal to 0 minus 1, 1. If you do the composition of f with r2 of t, I'm just going to write out what the vector ends up being. This ends up being the vector e to the t, e to the 1 minus t, and then 1 minus t. And so if you compute this integral, so this integral over C2 of f dot dr, if you do the dot product of these two vectors here, you're going to get 1 minus t, and then that's going to be minus e to the 1 minus t. So this will be equal to the integral from 0 to 1, 1 minus t minus e to the 1 minus t dt. And this ends up being equal to 3 over 2 minus e. So I'm going fast, but I mean, this is exactly what we just did, except with a little bit different numbers. So, I mean, if you can figure out the first part, you can figure out the second part, and you can also figure out the third part. So the third part is telling us we're going from 0, 0, 1 to 1, 0, 0. So that tells us that our parameterization is going to be equal to t, 0, and then 1 minus t. Again, when t is equal to 0, you get 0, 0, 1. When t is equal to 1, you get 1, 0, 0. So that works out. If you take the derivative, this will be equal to 1, 0, minus 1. And then if you do, let's see, f, I'll just write out the composition, why not? If you do the composition of this, this is going to end up being equal to e to the 1 minus t, 1, and then t. So if you do the integral over C3 of f, this is going to end up, so you do the dot product of these two vectors. So it's going to be e to the 1 minus t subtracted by t. So this ends up being equal to 0 to 1, e to the 1 minus t dt. If you compute this integral, it ends up being minus 3/2, and then it's going to be plus e. Okay, and so if we add all of these terms together, that will give us the total integral over this path, right? So if you take the sum of all three integrals, it gives us the integral we wanted to compute in the first place. So let's do that. So the integral over c of f dot dr So we just take the sum of all components. So it's going to be e minus 2. That's going to be plus this 3/2 minus e. And that's going to be plus minus 3/2 plus e. So you can see two of these parentheses are going to cancel out. You have 3/2 minus 3/2. You have minus e plus e. So this ends up just being equal to e minus 2. Right, so this is kind of a tedious problem. I don't really like going through it because you're just doing the same thing over and over again. But you might have to do this once on next week's homework, if I remember correctly. And then later on, you'll have a better appreciation for Stokes' theorem because it gives you a much easier way of computing the same integral. Okay, before I move on, are there any questions about this example? Any part? Yeah. No. Yeah, and plus, like the next exam, you'll have Stokes' theorem, so you're kind of doing it wrong if you're doing it this way, is what I would say. Like you could do it, but it's like I don't want you to do it. So, yeah, this isn't something you'll have to do on the exam, but I guess it is a way of doing a problem on the exam. Any other questions? Okay, so there's one more thing I wanted to touch on before going on to conservative vector fields, which is section 16.3. This is just kind of the main application of the vector line integral. I think this is just something, I haven't taken advanced physics or anything like that, but I know these vector line integrals show up all the time. And so what are these vector line integrals telling us in terms of physics? So we return to something called work, which if you're in my Calc 2 class last semester, we talked a little bit about work and how you can compute it using integration. So in physics, work refers to the energy expended when a force is applied to an object as it moves along a path. So when you see the word force, you should be thinking about the vector field. And then when you see like an object moving along the path, you should be thinking of our parametric equation, or like the curve C that we're integrating over. And so by definition, if we just have a straight line segment from P to Q, like we have pictured here, the work W performed along this straight segment is going to be, like we're assuming it's going to be applying a constant force F at an angle theta. And it's going to end up being the following computation. So it's going to be the tangential component of F multiplied by the distance. So I talked about the tangential component of F yesterday. In mathematical terms, it's the projection of your vector F on the unit tangent vector at your point P, like we have here. This is probably a better picture to look at, actually, this part right here. So this is the unit tangent vector. You can see it's a little bit short compared to like where this dotted line actually intersects with this green arrow. So like this red arrow is a unit tangent vector. This green arrow, which is in the same direction, but it's a little bit longer, is a tangential component of your curve at the point PI. Okay, so you don't have to have like a great understanding of this or anything, but how work is computed is it's a tangential component of F times the distance. Again, the tangential component of F is the dot product of F with the unit tangent vector. And so we can rewrite this dot product as the magnitude of F times cosine theta. We did this derivation yesterday. And then this is multiplied by the magnitude of this line segment. And so if we're going to be doing integration, what we're going to be doing is we're going to be considering smaller and smaller line segments until they get infinitesimally small, and then we'll do a Riemann sum. And so you can go through that thought process, but what ultimately ends up happening is that when the force acts on the object moving along a curve C, it makes sense based off of this definition to define the work W performed as the following line integral. Because remember, this line integral is really just the same thing as integrating F dotted with T on the curve C with respect to the arc length, right? This is really how it's defined. And then from here, you can say this is equal to the integral from like A to B of F of RT dotted with R prime of T. So this is like the scalar line integral of the tangential component. Again, you don't have to have like a great understanding. I'm just trying to explain things in case people are interested, pretty much. Okay, and so what's really being said here I should have included a graphic, is if we have the following curve. So this is how to interpret these vector line integrals in terms of these, in terms of work. Okay, like what I'm really saying in layman's terms, without all the like math jargon or anything, is if we have a curve oriented in the following way. Let's relabel the point. So this is P, this is Q, and we have some vector field F, which is like a vector field, and it's pointing in all these, like, it's pointing in this uniform direction, I suppose. If you have this situation where the orientation of your curve flows along with the vector field, like what I'm really saying is that the work is going to end up being positive, which means that this vector line integral of F over C dr, this is going to be greater than 0. And if you flip the orientation of the curve, so that way it was going to be in the opposite direction, like this, that means it's going to be negative instead. So like how you interpret this is it's really just saying, like, is your curve, is the orientation of the curve flowing with or against the vector field you're looking at? If it's with, it means that the vector line integral is positive, because that means the work is going to be positive. And if it's against, that means your vector line integral is going to be negative. So that's, I mean, there might be, I think on the final last semester, I just asked one problem where you had to determine whether or not the sign was going to be like positive or negative. So if you have that understanding of like how it relates to the flow of the curve versus the flow of the vector field, it should be easy points. Right? Okay. Yeah, and so what else I want to say? So often we're interested in calculating the work required to move an object along a path in the presence of a force field F, such as electrical or a gravitational field. In this case, F acts on the object, and we must work against the force field to move the object. And so the work required is the negative of the line integral above. So if you're looking at the work performed against F, it's going to be -1 multiplied by this vector line integral. So if you have more knowledge of physics, you can probably talk more about like what's going on and like how to interpret work. But to me, this is like a bonus, I guess. I'm more interested in knowing that you know how to compute these things more so than like understanding all the nitty-gritty details. So we'll just do one example of this. Like really what this means for you is I can ask you to compute the work and you have to know what that means. If I'm asking you to compute the work, it just means I want you to compute the vector line integral. And then when we do surface integrals, I can ask you to calculate the flux, and that just means calculate the surface integral. Anyway, so we'll go through one example. For this one, it wants you to calculate the work performed against F. And moving a particle from P is equal to 0.111 to Q, which is equal to 482, along the path given by R of T is equal to T squared, T cubed, then T in meters, and T ranges from 1 to 2. And then the vector field is given by the force field F is equal to x squared minus c, and then minus y times z inverse. Right, and so what we want to do, because it says it wants you to calculate the work performed against F, it means it wants you to calculate this vector line integral, and then it wants you to multiply by -1. That's where the word against is manifesting, is you're going to multiply whatever you have by -1. And so, I mean, if we want to calculate the vector line integral, that means we need to find the composition of F with R of T. So this is going to be F of T squared, T cubed, and then it's going to be T. And so if you look at F, what we're doing is we're taking the first component, X, and then we're squaring it. So the first component of our new vector field will be T squared squared, which will be T to the 4th power. The second component of F means we're taking the third component of our input and then we're multiplying by -1. So this is going to be minus T in the second component. And then the third component is minus Y times Z, or the reciprocal of Z. So you're taking minus T cubed and then you're really just dividing it by T. So that'll give you a minus T squared. So this is the composition of F with R. And then it also, like, we need to also compute what R prime is going to be. R prime is just a bunch of polynomials, so it's not too bad to compute. So you just go component wise. The derivative of t squared is 2t, and then you have 3t squared, and then you have 1. So this is going to be 2t, 3t squared, and then 1. And then we also, kind of the last thing we need to do before integrating is we can take the dot product. Like we want to take the dot product of these two things. If you take the dot product, this is going to be t to the 4th power times 2t. So that's going to be 2t to the 5th power. You're going to have 3t squared times minus t, which is minus 3t cubed. And then you have a 1 times minus t squared. So that would just be minus t squared. And so all that's left is we just need to integrate this equation where t ranges from 1 to 2. So it just reduces to a Calc 1 problem now. So the work against, this is going to be equal. So again, because we're doing the work against instead of just the work itself, that means we multiply by minus 1. So this is going to be minus 1 times the integral from 1 to 2 of 2t to the 5th power minus 3t cubed. And then this is going to be minus t squared dt. So this is just a Calc 1 integral, right? So this will be like 2 over 6 times t to the 6th power minus 3 over 4 times t to the 4th power minus 1 over 3t cubed. And then you plug in t is equal to 1 and t is equal to 2. And what that ends up giving you is it ends up being equal to 89 over 12. Right, so you can compute the integral and confirm that's what it ends up being equal to. Again, this is just something from Calc 1, so I'm not going to spend like 5 minutes going through the computation. But what's important is you know kind of what you need to find, like the composition, the derivative, and then the dot product between the two. It's the main difference that's happening now. Any questions about this example? I'm not gonna lie. I don't. Wouldn't it be
On an exam, would we have to?
No.
Okay.
I mean, I don't really. Would it be like joules? I don't know what the unit for work is going to be. I don't know if it's like joules or it's like bad. I should know. I'm not like a physics guy. I don't really know, to be completely honest. But it's something I should have looked up before. It's like something over meters. It's probably joules over meters or something. But any other questions about this example? Yeah.
So we don't need to use a meter.
Oh, yeah. It's kind of if it didn't give you, yeah, we didn't really have to use P and Q for this one. Sometimes it is important. Like if it didn't tell you like what R of T was, you would have to come up with a path that starts at P and then ends up at Q. And the integrals aren't always going to be path independent. So sometimes the choice of path is going to create a difference. We'll talk more about that later on, but yeah, because it already tells you what R of T is. You don't really have to think about P and Q. What matters is that if you plug in T is equal to 1, you get P. And when you plug in T is equal to 2, you end up getting Q. Yeah, but we'll see, like actually in the next section, we'll see, like sometimes the points do matter. Any other questions? Okay, so there's another page to this. We're just gonna skip it. We'll talk about flux later on, but it'll be in the context of surface integrals instead of trying to define it in terms of a vector line integral using like the unit normal vector. So we're gonna skip this section, or not this section, like we're gonna skip this page for now, and we'll talk about flux in a different context later. It's kind of a niche way of defining it, is the way they do it on that page, so we're fine with skipping it. And instead, we're going to move on to conservative vector fields. This is an important section in that this is the first generalization of the fundamental theorem of calculus that we're going to see. This is really what we're building towards in chapter 17, is thinking of like, what are all the ways in which we can think about the fundamental theorem of calculus in terms of like gradients and vector line integrals and double integrals and triple integrals and surface integrals. So like just how do all these things relate to one another pretty much. So in this section, we study conservative vector fields in greater depth. Do I have any reminder of what a conservative vector field is? Okay, so just as a reminder, a conservative vector field is the following. So we have F. This is from section 16.1, but we did that last week, so maybe you don't remember. So we say F is a conservative vector field when there is a potential function, or I should say there's a scalar function, little f, say like f of x, y, z. And the important thing about a conservative function is that the gradient of f is equal to the vector field, right? So we take the scalar function. If we do the gradient of f, that gives us a vector. And if that vector ends up being equal to the vector field, that means that the vector field is conservative. And so the important interpretation of what it means for this to be like a conservative vector field is what we're effectively saying is that this little f is an antiderivative of big F, right? This is how we were thinking about things. Let me see if I can find the notes that we did last week. So I kind of made, I don't know if a big stink of it is like the right word. It sounds like a negative connotation, but I was like yapping about it for a long time, right? So this is like, I was saying like this little f is kind of like a potential function for f in the sense that like big F is equal to the gradient of little f. It's kind of like saying the derivative of little x or little f is equal to like big F right here. And we know from the fundamental theorem of calculus that if you take the integral of f of x, that must mean that it's going to be equal to f of b minus f of a, right? I think I have that mixed around actually. Anyways, so that's kind of the idea of what we're doing. And now I'm lost. Okay, I just need to scroll down. Okay, so this is like how we're thinking about things. Anyways, and so we want to have like a nice theorem that pretty much says, like gives us the fundamental theorem of calculus here. Oh yeah, I kind of was thinking about things backwards a little bit. Okay, and so where was I? Yeah, so we're going to study conservative vector fields in greater depth. One important property we'll see is that the vector line integral of the conservative vector field around a closed curve ends up being equal to 0. So like we're going to be looking at, I guess, vector line integrals over paths, but also over oriented closed curves. So I just wanted to have, I guess, some notation I wanted to establish. So when a curve C is closed, what that means is the beginning point is the same as the end point. Like a circle is an example of a closed curve. We have a special notation for the line integral when we're working over a closed curve. So we refer to the line integral of any vector field f around a closed curve C as the circulation of f around C. And so what that manifests into, like with respect to notation, is the following. So we just take the integral symbol and we draw a circle through it as follows, right? So if you see this notation, that means we're doing a vector line integral over a closed curve C. So like this circle here indicates that the curve is closed, right? Like it begins and ends at the exact same point. And so it doesn't actually matter what point we take as the starting point when we have a closed curve. And so this is the important result from this section. It says like the first result, and what it's really saying, like, so there's two parts. The first part is really going to be a generalization of the fundamental theorem of calculus, right? Like this should look like the fundamental theorem of calculus that we have. And it also is saying that it doesn't matter like what curves you're looking at or integrating over. It just is dependent on the points that you're taking into consideration. And then the second part of this theorem just tells you that if you're on a closed curve, this vector line integral ends up being equal to 0, right? So really we're saying the first result establishes path independence of conservative vector fields. So if you look at this picture, if we have a point P and a point Q, we can take this path or we can take this path. And so what this theorem is going to tell us is that it doesn't matter which path you end up taking. The vector line integral will end up being the exact same. And I mean, I pretty much already said everything. Before even formally writing out the theorem, I've kind of said everything I want to say about it for now. But let's formally read out the theorem. So this is a fundamental theorem for conservative vector fields. So the big part is 1. The second part is just a direct corollary of the first part. And so all we're going to do is we're going to assume that big F is a conservative vector field, meaning there exists a scalar function little f such that the gradient of little f ends up being equal to big F on a domain D. And so the first part is the important part. It tells us that if R is a path along a curve C, so you should be thinking R is a parameterization of our curve C from P to Q in some domain D. Then we have that the integral, the vector line integral over our conservative vector field ends up being equal to F evaluated at Q minus little f evaluated at P, right? So you take this function, little f, and then you just plug in the endpoint, and then you subtract by that the beginning of the beginning point. So this is pretty much just the fundamental theorem of calculus, right? In particular, this tells us that F is path independent because this quantity doesn't rely at all on your parameterization. It only depends on your scalar function and the points that you're plugging in, Q and P, like the beginning and the end points. It doesn't rely at all on the actual path. And then the second part says that if we have a closed curve, like if C ends up being a closed curve, which means that P is equal to Q, then we have to have that this vector line integral is always just going to be equal to 0. So before going through an example, we're going to prove this theorem, and it really isn't too bad to prove in complete honesty. It just relies on the fundamental theorem of calculus. So we're going to suppose 2 things, or just one thing actually. We're going to suppose that our vector field F is conservative, meaning that it's equal to the gradient of little f on our domain D. And so let's just compute this quantity, right? We're going to start with this integral, and on like after some work, we want to be able to get this quantity that we have. And it's really just going to rely on the chain rule that we established in section 14.6, right? So if we start off with this integral of f, this vector line integral of f over our curve C, we know f, big F, is equal to the gradient of the scalar function. So this is equal to the integral of the gradient of f dotted with dr over the curve C. So I'm just making this substitution going from here to here. That's all that I'm doing. And then by definition of the vector line integral, we know that this is going to be equal to really the dot product of the gradient of f evaluated at RT with the derivative of R of t. And then this is going to be over the interval from A to B, right? So this is how we've been computing the vector line integral, is you do the composition of your vector field with the parameterization, and then you dot with the derivative of your parameterization. So that's all I'm doing, going from here to here, just using the equation we've been using today and then yesterday as well. And then the big observation is that we know that, I mean, it's kind of maybe a little bit fuzzy, but we saw in section 14.6, I think, that this is really just the chain rule applied to a vector composed with a path, right? Like we saw in section 14.2 or 14.6, that inside of this integral, this is really the derivatives with respect to t of f composed with r of t dt, right? So this is kind of like the chain rule, right? Like the derivative of f composed with rt ends up being the gradient of f evaluated at r of t, and then you multiply by the derivative of the inside. So like this is a form of the chain rule that we've looked at in the past. And so, I mean, at this point, like we have an integral of a derivative, and we're just integrating over some interval, right? And so we can use the fundamental theorem of calculus here. So if you use the fundamental theorem of calculus, this is going to be f of r b, and then this is going to be minus f of r evaluated at a, right? I'm just plugging in t is equal to b here. Like I'm canceling out the integral and the derivative and then plugging in t is equal to b. and then subtracting by what you get when you plug in t is equal to a. And then all that's left is, we know where our path, like r goes from p to q. So f of rb, that's the endpoint of your path. So that's going to be f of q. And then r of a is the beginning of your path. So that's just going to be p. So that's going to be f of q minus f of p. Right, and so this gives us exactly what we wanted, right? So this vector, as long as f is conservative, if you do the vector line integral of big F, it ends up just being this difference that we have here. Right, so we'll see examples of this later on. Like a concrete example will probably make this easier to understand why this is so helpful. That's just the proof of this first statement. And again, this is really just saying we only depend on the endpoints of the path and not the path itself. And I guess also the scalar function that we have. All right, and so that's the first part. Then we just have the second part. Can anyone say why the second part ends up being true based off the first part? Like why is, if we do this vector line integral over a closed curve, like why is it going to end up being equal to 0? Yeah, go for it. Yeah, I mean, if we have a closed curve, that means the beginning point and the end point are equal to one another. So P is equal to Q. And so if it's a closed curve, then if you do the integral of dr, and then because it's a closed curve, you can do like the circle through the integral to be more specific about the kind of curve you're looking at. This is going to be equal to f of q minus f of q, right? The beginning point and the ending points are the same. So this is f of q minus f of q, so that's just equal to 0. Right, we're effectively saying just p is equal to q, so this becomes q, and you're just subtracting the same number from itself. Okay, so on the, I think on the final, I had 1 or 2 problems where you had to make use of this theorem. That's an important theorem to understand, right? Just as the fundamental theorem of calculus was important to know how to do like pretty much any antiderivative. So this is like a way of making your life easier if you understand what's going on. Let's just go through, let's see, do I have time to go through this next example? I think I should have enough time to go through this next example. So this next example is going to be making use of this fundamental theorem of conservative vector fields. And so we're going to let f, big F of x, y, z, this is equal to the following vector field. This is 2x times y plus z in the first component, x squared in the second, and then x in the third component. So in order to make use of the fundamental theorem of conservative vector fields, we have to actually show that this is a conservative vector field in the first place. So the first thing it wants us to do is it wants us to verify that f of x, y, z, which is given by this function here, actually ends up being a potential function for big F. This just means take the gradient of little f and show it ends up being equal to big F. And then once you know that, it wants you to evaluate the vector line integral of big F, where C is any curve from that starts at P and ends at Q, or P and Q are as written, right? So the first part, I just want you to show that F is a potential function for the vector field big F. So you just take the gradient of big F. Again, the gradient is just like the partial derivatives with respect to x, y, and z of little f. So if you take the partial derivatives, this is going to be 2x times y plus z in the first component. Integral or partial derivative with respect to y will just give you x squared. The partial derivative with respect to z will just give you x. And this is equal to big F, right? So voila, there it is. Like the partial derivative of f ends up being equal to big F. So that means big F is going to be a conservative vector field. And so once you know it's a conservative vector field, you can apply the fundamental theorem of conservative vector fields in order to calculate what this vector line integral is going to be. So if we want to calculate this vector line integral of our curve C, where C goes from the point P to the point Q, by the fundamental theorem of conservative vector fields, really this is going to be equal to the following. I mean, you don't have to write this out. I'm just writing it out just because I want to make it clear that we know that big F is equal to the gradient of little f. And so this is just going to be equal. So by the fundamental theorem of these vector fields, this is just going to be equal to f of q minus f of p. Where we can be a little bit more specific, right? This is going to be f of 2, 2, 3 minus f of 1 minus 1, 2. So I'm just making use of the points that they give you in the beginning of the problem. So computing this vector line integral ends up just understanding like what are these two values? Like what do we get as outputs for these two functions? And then you just subtract them. So should be like, it's much easier than, I mean, it wasn't that bad before. I mean, before we're just doing a composition, doing a derivative, and then doing the dot product. But this is still a lot easier, right? Right, so let's see what ends up happening. So if we plug in these points into f, so f of 2, 2, 3, that's going to be a 2 squared times 2 plus 2 times 2, or times 3 actually. And then that's going to be minus what we get when we plug in x is equal to 1, y is equal to minus 1, and z is equal to 2. So that's going to be 1 squared, and then that's going to be minus 1. That's going to be plus 1 times 2. And so this ends up being equal to 14 minus 1. Or it ends up, I'll just say this ends up being equal to 13. Right, so that's all you have to do. Like once you have the conservative, like once you know it's a conservative vector field, you can then apply the fundamental theorem for conservative vector fields. And it's as easy as just finding the difference of these two values, right? So we'll continue. I'll stop there. I feel like it's a good place to stop. We'll talk more about the fundamental theorem of conservative vector fields tomorrow. And then tomorrow I'll also pass back the exam and I'll go through some of the problems on the exam that you had last Friday. So if you have any questions, I'll stick around for the next couple of minutes. Otherwise, I'll see you tomorrow. Yeah.
Would you apply it to like the real world problem?
I mean, anytime, again, I haven't like seen it too much in applications, but I mean, if you're asked to compute like work or something along those lines, or like the amount of force, like whenever you see like a vector line integral, okay, let me stop the recording first. I think I have to do it on here. Yeah, whenever you see a vector line integral, or whenever you see the